Alright, so now that we've derived the governing differential equations for the heights for both tanks, we're going to go ahead and solve our IVPs using our collaboratory. So we're going to, first we're going to solve them, and then we're going to plot our results for the given time range with our given values. So first thing that we're going to do is get our, we're going to go from SciPy integrate, since we're going to be integrating our differential equations. We're going to go ahead and import our solve IVPs for our initial value problem. Okay. Next, we're going to go ahead and import numpy as np, as always. And then, since we'll be dealing with interpolations, we're going to go from scipy.interpolate and then import our function for that, which we will use later. Okay. And then we're going to go ahead and get our plots. So from plotly.subplots, we're going to import make subplots. Okay. And then finally, we're going to import plotly.io as PIO. Alright, it's good from there. Let's go to our next line. Make sure everything's good. Okay. Looks like it's loading. Okay. Yep, should be good. Then we're going to go ahead and we're going to define our dHdt that we had already solved for. So we're going to just call that dHdt. And we're going to be using t and y as our dimensions. Okay, and then we're going to go ahead and call our h1 and set that equal to y, and then in brackets. Brackets are super important. Not those ones, but these ones. There we go. Okay, and then our h2 is going to be called y2. Alright, and then for our flows, this is in between tank 1 and tank 2, called Q1 E2. Q12 is going to be equal to same thing that we'd already written, alpha. And then we're going to multiply that by our square root function. So, and then we know that that is h1 minus h2. And then we'll do the same thing for tank 2. So tank 2 is going to be equal to alpha. Okay, so that should be alpha 2, which means this one should be alpha 1. Yep, alpha 2. And then same thing times our square root function. And then this one's just h2. Alright. Now we're going to go to our dh1 over dt. And we're just going to call that dh1 for simplicity's sake. Set that equal to our qn as a function of t minus Q12, and then from there we're going to divide that by the area. Okay, no, not the alpha, the area. There we go. Okay. Alright, so then we're going to do the same thing for our dh2. Set that equal to our Q12 minus Q2 for our flow rate going out of tank 2, and then we're going to divide that by the area. Hey, it worked that time. Alright, everything looks good there, and then we're going to go ahead and return those values. So be dh1 and dh2. And we'll go ahead and run that, make sure everything's good. Alright, let's move on to our next line. So we have what we needed there, and we'll go ahead and move on to we'll get to our interpolation problem, but we'll set some more parameters. So we're going to plug in our alpha 1, set that equal to 0.5. We're going to get our alpha 2 as well, which we know from the problem is equal to 0.25. We're going to get our area for tank 1, which is 1. We're going to get our area for tank 2, which is 1.5. We're going to get our height, which will be equal, no, not that one. This will be, we'll call this HI. It's going to be in brackets from 2 to 1.5. And then we'll go to our t-end. And our t-end is basically our simulation time. So we're just going to set that equal to 100. Cool. And these are just some more info on the parameters that we'll be using. So we're going to go ahead and do our qin values. So that's going to be qin underscore v. And then that will be from 1 to 1.5. And then 1.5 there. Space that. Okay. And then we'll do the same, our qin values for t next. It's going to be equal to 0.0 to 50. And then I'll be using our t-end function. And then finally, we're going to be using that interpolation function, which will be set equal. So qn will be set equal to our interpolation. And then it'll be from our qn underscore t to our, so that's our time, which will be the x, our values, which will be our y, and then the kind is going to be defined as previous. Okay, we have those. Looks good. All right, now we're just going to go ahead and solve it. So we have our parameters. So first we're going to say our resulting height. We're going to be trying to figure out the resulting height at any time that we need it. So we're going to call res. It's going to be equal to our initial value problem function, which we'll be using dHdt, and then we got from 0 to t-end, and then we got hi method. It's going to be our Rideau method. And then one more thing, we have to set our dense output to true. Okay, looks good. Now we're gonna do our linspace function. We're gonna set t equal to that. So our np dot linspace. And that's going to be from 0 to t-end, and with 100 points. Okay, looks good. And let's go ahead and run that. All right, so go ahead and run that. Okay, it looks like our I see. So we did not define. I messed up this. It should be dHdt. Yeah. Alright, let's try that again. Well, alright, looks good to go. So we'll keep going on this line, and we're gonna move on to our solution to give us our array. So we're gonna say our SOL is gonna be equal to res.sol function of t, and then our t is gonna be set equal to, or I'm sorry, not t, fig is gonna be set equal to make underscore subplots, and then rows are going to be 1, and then columns are going to be 1 as well. Okay, so have that one. I'm going to go ahead and do a fig.add scatter plot function. So add scatter, set x equal to t, y is equal to sol 0, name is equal to, let's call it h1. Okay. Next we have our fig.add scatter function. Oh, I forgot a period there, I believe, or underscore. And then same thing for this x. It's going to be set equal to t, and then this time would be our solution of 1. And then call that h2. Okay. Oops. Alright, now we're going to update the layout and set the dimensions. So update layout be a width of 500 and height of 400, and then not that 400, say the legend orientation is going to be equal to h, our legend underscore x is going to be equal to 0.5, and our legend for our x anchor is going to be in the center. Okay. Next, we're going to do our legend y. Set that equal to -0.2. Our x-axis title is going to be equal to time s in seconds. And then our y-axis title is going to be called h1, h2. So it's going to be equal to h1, h2. Our y-axis show grid is going to be true. Our x-axis for the vtake is going to be equal to 10. And then our overall title, we're just going to call it 2 tanks in series. So 2 tanks in series simulation. And then our title of our x-axis will be 0.5. Alright, it's a long line. Next we're going to do our template. Almost done. It's going to be our PI.